My name is Paulo Dias. I'm from Underwater Systems and Technology Lab, here from FEUP. And I'm going to give a brief overview of our toolchain for unmanned systems. Okay, so our toolchain is basically composed of three components, which goes from the software that's running inside the vehicle, so the dune on the bottom. So it's the uniform navigation environment. It's C++ and it runs inside the vehicles. On the top, we have the command and control framework, which serves the monitoring and controlling of the unmanned systems. And then on the middle, we have a layer which is a message-based protocol that is called intermodule communications. That is basically a set of messages that enables the systems to talk with their command and control units. Okay, so basically we started at the lab with a system that we bought from Udsol, which is now Hydroid and Remos. And we were not able to do much thing without changing. Or we could, if we have money, we could buy the changes, but it was not possible for us to do the things that we wanted. So one of the first things that we start to develop was command and control, which allows us to create a more reliable planning platform, which on that days and still today it's a text file, which is easily you can input mistakes on it. You don't validate it by just looking at the text, and we basically create the Neptus. Then we created the onboard software also. Because we wanted to have control of the platform, so we took off the hardware and replaced it with our own hardware. So we also needed some ways to control that hardware and expose it to the outside. And so that basically was born the LAUV, and from then we just been developing more and more, and it's basically expanding. And right now it's a commercial platform. So basically our toolchain is a complete software solution for autonomous systems. It has a lightweight operating system, an API to interact between software modules, onboard software, a command and control unit, and mission review and analysis. So those are the components of basically the toolchain that we have. So once again, why do we start it from scratch? At that moment, which is kind of 2004, the Remos software was kind of based on Unix and pre-ISO C++ 98, so the code base was developed and maintained poorly, and freely available software at that time had some shortcomings. So it was highly experimental, cumbersome, and impossible to use on embedded systems. The command and control software was primitive, and kind of we disagree with the architecture and design choices that in those days were. And also, even on our initial code, there was a lot of comments like this. So it was created by someone, updated some years ago by another person, and kind of get changed, and it was kind of hard and harder to change and introduce new features. And so this is a little bit of the structure of the toolchain. So we have the vehicle, the GLUT, which is the operating system, so it's Linux based. And inside of it, we have the onboard software, the Dune, which uses the IMC message protocol to talk with a common PC and in Neptus, so we could monitor and control the unmanned systems. So let's start with the GLUD. So it's a minimum GNU Linux distribution focused on embedded systems. So it's a small footprint, a fast boot, so 2 to 5 seconds, depending on the target machine and peripherals. And the target machine binaries are cross-compiled, so you can compile it on your PC and upload it, the code to be run on the target computer. So it creates a reproducible root file system for a given target and supports several architectures. What was the motivation of building these operating systems? So the time to build was live software in embedded systems. It's unbearable. So if you don't want to compile the code on the target computers, which have less memory and CPU power. So you want to have an embedded systems that you can compile it and kind of test it in your own PC, and then cross-compile it and upload it to the computer, to the target computer, and execute it. So we support kind of the ARM x86 base and MIPS. So you can have those GLUD operating systems available for those platforms. In the middle, it's the Intermodule Communications API, which is a message-oriented protocol. So basically, it doesn't depend on the medium. So you can use it in TCP, UDP, acoustics, Iridium, whatever, as long as you can serialize it, and you have several ways of serializing it. So we have one XML document which defines the messages, so the H fields, and with it, it's kind of also not only the specification but also the documentation base for the messages. So you can generate the documentation, and you can generate bindings for C++, Java, and there is not so well tested for Python also. So you can serialize it with JSON, XML, but we usually, for the systems, we use it in a binary form. So you can serialize it, you can log, and basically the serialization format is a format that the vehicle stores, and you can open and explore those collected data. So there are some different layers on a typical vehicle. So you have plan control, you have vehicle control, maneuvers, guidance, navigation, sensing, actuation, networking, storage. And so each one of these layers has a set of messages that you can use. And those messages can be used for inter modules inside the vehicle, but also can be passed and to the outside for the command and control, which we'll be seeing later. So each system has an address, so it's has a unique address, and from those addresses you can kind of see which type of vehicle that there is. If it is a UEV, AUV, ROV, if it is a command and control unit, which is the Neptus, or a sensor like a drifter or something like that. So each system has a unique address, and there is a subset, which is the subsystem or entity ID, which is the module inside your vehicle. So you have a navigation task or process, and that component has an address inside the vehicle. So you know which system produces each message. Which is the anatomy of an IMC message? So you have a synchronization number, which defines the set of messages that are available, so you know a priori how to deserialize it. So it marks the beginning of the message. indicates the protocol version and allows for endianness detection. So you can use big endian or little endian, and with this serialization number, you are able to see if you have to deserialize it as big endian or little endian. So everything is it's the starting point for the serialization of that messages. And also you have the identification number of the message, which is unique, the message size, and the timestamp. So basically this is the header of the message. So you have the source address, which is the address, the IMC address of the system that is producing this message, the source entity, which you also see that is the subcomponent that created that message, and then you can have the destination address, which is the destination of for another IMC system that you want to send this message to, and also if you want to address a subsystem on another system. And you have the message-specific fields, and at the end you have the CRC, which is 16 bits. And this is an example of a message. So this is the message 263, which is a for temperature. And you can see the description, which is going to be generating the documentation for this message. And you have the fields. In this case, it's only one field, which is the floating point 32 bits. And you can see a name and the unit. So also the unit is merely for documentation purposes. And this is a very simple message and definition that you are able to define and create the bindings for any language that you want. Now for the software that runs inside the vehicle. So this is the Dune. And so it's written in C++, and we use it on our AUVs, UEVs, ROVs, ASVs, data loggers, and basically any subsystem that we create on our lab. It's related to logical operators are isolated from each other, so it's basically a task which you can see as a separate thread that communicates between the modules in IMC messages also. So internally you can send to the bus IMC messages that you can set up communication between some modules of these systems. So you can use this with TCP, UDP, acoustic modems, Iridium, and GSM. And it has its own logging, so it's basically the serialization of the IMC messages that are logged. And the interaction with sensors, actuators, and power devices. So each one of these, you have tasks dedicated to these kind of sensors. You have controllers for attitude, speed, manual operation, guidance, algorithms, maneuvers. And then you can basically create a configuration that basically defines your system. It's an INE file which says which tasks are to be run and which from which configuration it has to be configured. So it basically supports those architectures. It runs on Linux. It's basically, we use it on our GLUT, but you can compile it also for different sets of operating systems, from typical Linux to Windows, Unix, Mac OS. We usually use it only on the GLUT, so Linux-based, and he has some also supporting for some serial port I2C, CAN, and so on. So you can, out of the box, you can create those tasks and use it for communicating with your sensors. So the required software to use this Dune, it's Git, which is the source control, which you can find it the code on the GitHub. CMake, C++ compiler, Python interpreter. It's basically for some scripting and the generation of the bindings for MC. And you can use whatever. You can use Eclipse, the Microsoft Visual Studio, or a text file for the creation of the tasks. Um, so these are the kind of the required software for you to use. On Ubuntu, it's kind of easy because you can simply have the installation mostly done. In Windows, basically, if you have to install it, this software by hand, and you can also use it the Mac OS to develop these tasks. And this is the simple example of the available tasks that you have. So you have a core library, which has the core bare bones that you can use on your tasks. You have the core functionality that is the task management, the message bus, the configuration, and the tasks themselves. And then you have the hardware and simulation sensors. So there are tasks that connect to the sensors and place those values on the bus, so the upper layers can use them. And then you have a set of generic tasks that includes the navigation, guidance, maneuvers, monitoring, supervisors, controllers, and transports that you can reuse, or if you need to create some specific tasks, you can create it based on this or from scratch. And once again, these are the resources that you can use. So the Dune is it's placed on GitHub, so you can get it. The documentation is also online. We have a mailing list that you can that you can use if you have questions. So it's the LSTS toolchain, Google Groups, and that you can even now you can use that mailing list to ask questions. And so we also do some nightly builds, so to see if there is any errors on the code. We also now for the command and control. So this is Neptus, which it's the upper layer for the command and control part of the toolchain, and supports typical mission lifecycle. So the planning, execution, and review and analysis. He has a modular architecture through plugins, so you can reuse some components, or you can add your own specific visualizations, communication protocols, data visualization, or even maneuvers. Specific to your systems, and basically it's kind of just adding some charts which enhance the available components on Neptus. So you have the planning, which is composed by a console, an operating console. It's and then the execution, so you can monitoring, which is also on the console, and then you have the review and analysis, which you can add visualization and add and view the data or export the data. So I'm going to show you a little bit, kind of for running it, so you can see it more clearly. So a typical console, it's the base where you start to use the toolchain. So this is a map which you can choose the layers that you want to see it. So you can get the data from Google Maps or OpenStreetMap and activate it. So those tiles get cached, so you can use it offline for later if you don't have internet. So you can also add nautical charts, which is kind of have more information. So you can extract data from it, like the soundings. You can also add your own obstacles or features on a map. So if you want to draw some areas of interest, if you see some boat that you want to avoid or something, you can add those features to a specific map, and reuse it also for the components that are able to plan the trajectories. So this is an example of the addition of a point of interest. And also, you can define your own position on the map. And that is that can be reused or attached to some sensor that you have next to you. And then once, if you are on the ship, you can connect that your position to the position of the ship, and you'll be moving it with it. So you can also see that there is available systems, so active systems, and you can select a main system for you to operate or control. That doesn't mean that you don't see every system available and operated on it. So this is an example of the planning. So it's the base planning, which is a kind of a graph of maneuvers. And basically you can set up the parameters of each maneuver. In this case, you are defining the depth, the speed, and then you have kind of a payload part which is specific to each system. Just to see, there is a simple maneuver which is a point, but you can also have these typical patterned maneuvers that you can change visually or by setting the values by hand. And this is kind of the low mower, but you can also define some more patterns that you want to use based on the points, which for the vehicle you can, if the vehicle supports follow path, you can create these helpers for the operator that at the bottom will create a follow path for the vehicle, but you can edit and help the user not defining each point by hand, but simply generating it. Okay, so basically you can also set up these values for all the plan. So you can change the plan speed, the plan depth for all the plan, and also the payload settings for all the plans. So you can set up the payloads, in this case only the side scan. You can set up the same values to all of the plan or individually by each maneuver. And you also see this the plan statistics for the specific plan. And once you get this saved, you will see here on the tree, on this side, you will see that you have a set of plans that you can send to the vehicle. In this case, you just send it, so it's green, means that the same plan is also on the vehicle and on your side. If it is red, means that there is some difference on the plans. And if it's purple, means that only the vehicle has it, which you can download it from the vehicle, the plan to you. You can also see this kind of rough simulation. In this case, you can is using the payload and to see the footprint of the payload. If you have the altimetry or the bathymetry data, this footprint will be different depending on the if it is, for instance, side scan, you will see the footprint depending on the depth of the place. Which if you don't have this kind of S57 chart, you can enter these values by hand if you know it in advance or with some other source. So in this case, you are running the plan, and you will kind of see the vehicle path being drawn. Of course, as you probably know, once the vehicle goes underwater, you will have a little or no communication at all, which kind of, this is what we're going to see it from here. The vehicle goes underwater, and when we lose the connection with the vehicle, we start a simple simulation on our side. So you will see more or less what the vehicle is supposed to be doing. If you receive some updates from the vehicle through acoustics or SMSs or Iridium, this position, simulated position, will be fixed to the actual vehicle position and then restarted again. So you have an idea where the vehicle is and how much time it will take to end this maneuver. Which is specific to the vehicle. This is not supposed to be a very accurate simulation, but in the sense it helps you not to be wondering where the vehicle is when you need to know it. Another way of planning, so it's kind of just adding some references to the vehicles, and in this case you can see that we are controlling more than one vehicle at a time. So it's kind of just kind of have like something for the vehicle to follow, and you can adding these positions or these paths for the vehicle to follow. So here, it's basically the configuration of the console. So each component on the console can expose some configurations, which you can change and adapt and control and parameterize the components. So another way of planning, it's kind of just a click and send a command, which you can have, it's kind of a quick plan, so it's kind of just sending the vehicle away from some obstacle or vehicle or ship that is on the surface, which is kind of just a point and click, and the plan will be sent to that vehicle and execute. So it's kind of an emergency plan that you can send through to the vehicle. You don't need to have a Wi-Fi communication with it. So if you don't have Wi-Fi communication, Neptus will look around for systems that have communication, in this case acoustically, and send that plan through acoustic. And also, if you want, you can use Iridium or SMSs to send these plans. Basically, Neptus will look around for other systems that can expose some extra functionality. So you can also export plans to different platforms. So in this case, you can, for instance, export the plans to REMOS, so text file based. So you can export to those languages, and you can send it to that vehicle. You can see messages that are coming, so telemetry. And there is some extra visualizations which you can see the state of the subsystems. So in this case, each one of these lines is a subsystem of, in this case, this LUV Nautilus 2. You can also create some plots, real-time plots, which you kind of get some data by acoustic, but it's mostly more easy to see because you have more updates if you have Wi-Fi range to the vehicles. So you can also, these consoles are kind of, it's kind of a canvas which you can add and replace components, and with this addition and removing, you are basically composing the console to operate a system or a vehicle. So you can change the layout of the components. You can dispose the components on the console differently for using the profile. So you can change the visualization of the console. depending on the vehicle or the phase of the mission that you are. So in this case, it's kind of an FTP front end. So you can use the FTP to get the logs from the vehicle, or you can use this interface, which is kind of just getting each line on the left. It's a plan that was executed and the data that the vehicle collected. So you can get this data, and then you can open it on the review and analysis tool that we have. So I'm going just to briefly show you the review and analysis. Okay, so once you get the data from the vehicle, you are able to open it. So remember that this is not only the serialization of the IMC messages, but also the collected data by the other sensors. So there is some data that is vendor specific, and at least for the sensor that we have visualization for it. So one of the main visualization, it's the map. So you'll see what the vehicle it was doing on this, so you can replay it. So you can replay it in a different time, and you can see the data collected on top of the map. So in this case, you can see the attitude of the vehicle, and you can activate the sensor payload, and we are going to see a little bit in a moment the collected data. So you can see the replay of this mission, and there is some predefined plots that are created depending on the available data. So in this case, you can see some plots that are generated automatically, but you can inspect all the data that is collected, and in this case, it's the IMC messages that the vehicle logged. And you can plot any data that you want. So you can select, for instance, depth and see the plot. And you can also, if you want to correlate some data from one message to another, you can select multiple variables and plot the data together. So you can see in this case, is the estimated depth and the desired depth. As you can see, kind of the vehicle was following the desired depth. You can also depict the messages in a table, so you can inspect all the data individually. So you can inspect each IMC message, and all created charts are available on the visualization tabs. You can also export this data to MATLAB if you want, and to KML, so Google Earth. You can export to CSV and NetCDF, so there is some exporters that you can use to export the data for further analysis, or to, for instance, to give some client, in this case, in the KML. So you can see the creation of the mosaic for the side scan, in this case, which will be exported as Google Earth KML. So you can see the overlay of the collected side scan data. So, and this is the visualization for this side scan. This is the ImageNext side scan. So it's not the more cheap one. It's not very good in the sense that we have EdgeTech and Klein, which have more quality on the data. But this is an example of a side scan that can be inspected and generated. Um, so in this case, we are looking for, it was a container that kind of just drop inside the harbor, and we were trying to find the location of it so the authorities could retrieve it. So you can see that we can measure it and we can mark the feature on the map, and we can export it so we can give it to a diver to classify it. So in this case, you can basically just mark any feature that you want, give it the name, and you will see on the left the marks that are done. So this is another example. It's kind of also here in Porto. There is a World War II German submarine sunk. It was the end of the Second World War, and it's kind of the crew just sank the submarine and surrendered here in Portugal. So you can see the submarine is kind of intact. And this is the example, in this case is the EdgeTech side scan. And you can see that it's a well-preserved wreck. So there is a World War II submarine that if you want to do some diving, recreational, you can visit the submarine. Of course, for us it's more interesting to send autonomous systems to check it out. Okay, so this is an example, and another example. It's if you want to have a look, and we have some bathymetry. So we have some multi-beam data on the vehicles, and so you can see that we can overlay this collected data directly on the map. So you can see it on the chart, the data. Collected. Also, this is the example of a camera that is it's on the AUVs. You can apply filters. You can export also this data, and you can do some plugins to automatically classify some features on it. So this is an example of a camera. It was this is near Palermo, so in Italy, and it's kind of a really clear water, so there is no illumination necessary to it. Another example here, it's in the Azores. So we were asked to check some feature that a research vessel from the Hydrographic Institute saw, but because the ship cannot do very close to shore, they ask us to go there with a UV and collect some data on that mount that was appearing. You can see here the more red that is going to appear. It's kind of they said that it was created in 1 year time. They didn't have previous information on it. Probably it was garbage, but I guess at least for us seemed like it to be older than 1 year. So they kind of might be missing and didn't know altogether what was it. This data can also be seen in 3D, and then you can export it, the mesh, as a point cloud. And also, for instance, if you want to process this data outside this tool, or you can create your own plugin to do some extra processing of this data. So this is the same data that we saw earlier with the little C mount on the radar, and you can basically export this data to XYZ or point cloud. And then you get a little bit of plant statistics data, and you can export these small summary of this this mission to a PDF, which has a subset of those charts, and you kind of just can see the plots that are that were created for this mission, and then you can see the marks that we did on the side scan, which you can basically give to divers to classify it. In this case, it was easy; it was a submarine. But in the case, for instance, if it is a mine or a possible mine, you can the diver goes there and check the data and validates if it is a mine or not. And it's kind of this is more or less a little bit of overview of our tool chain. And if you want to interact with it, at least here in Marine URS, so you can get this some information on that Google Drive. So you can find it there, some helpers for you for the simulation in the loop for UAV for your projects. So you have there these slides also that was done the workshop in the Azores in the 2016. You also have a virtual machine image with everything installed for you to use. So you have indications or instructions to do the simulation with the LSTS tool chain, the software in the loop tutorial, which you can also use, or if you don't want to use the virtual machine and you want to set up in your machine, on your machine, you can use those scripts to create and install and run this simulation for your projects here. So any questions, you can also send emails to LSTS Toolchain, or you can ask us because we are kind of here to help you if you need. And any questions, you are welcome. Thank you.